In November 2023, off the coast of Japan, three V-22 Ospreys were preparing for what was intended to be a routine training mission following a refueling and maintenance stop in Iwakuni. Two of the Ospreys, Gundam 21 and Gundam 22, took off to practice aerial refueling with a C-130 and conduct a free-fall water jump, while the third trailed an hour behind in a support role. Gundam 21 carried 15 crew members, and Gundam 22 had 8. About 40 minutes into the flight, Gundam 21 received a message from Gundam 22, reporting 3 chip burn advisories but stating an intention to continue the mission. 10 minutes later, Gundam 22 began deviating eastward from its planned southbound route, and Gundam 21 received another message indicating a chip issue, but again affirming the mission would proceed. Gundam 22 was now heading toward Yakushima, a landing site 15 minutes away, despite closer alternatives being available. As Gundam 22 approached Yakushima, the crew contacted Tower Control, requesting to land on runway 32. When asked if it was an emergency due to traffic on the runway, the crew confirmed it was, marking the first and only mention of an emergency. While waiting for the runway to clear, the Osprey made a final right turn loop to begin its landing approach. At 300 meters above sea level, just 2 minutes from landing, the left nacelle caught fire. 6 seconds later, the aircraft experienced a hard roll, plummeted, and crashed into the water. The incident prompted the immediate grounding of all Japanese and American Ospreys. A search and rescue operation began at once, lasting 48 days. Some remains washed ashore, but the main fuselage and its 8 crew members were located a month later by divers 30 meters deep near the crash site. The V-22 Osprey is a remarkable aircraft, blending helicopter and airplane capabilities. It can fly at speeds exceeding 200 knots and cover vast distances without requiring the long runways needed by conventional planes, theoretically overcoming many helicopter limitations. However, this crash added to a series of fatal accidents involving the Osprey, raising questions about its safety, functionality, and the cause of the Japan incident. To understand these issues, we must explore the Osprey's origins, mechanics, and the investigation into this tragedy. The Osprey's development stemmed from a critical need exposed during the 1980 Iranian hostage crisis. Iranian militants had stormed the U.S. Embassy in Tehran, taking 54 hostages. To rescue them, the U.S. relied on our AV-53 Sea Stallion helicopters, which could hover for extractions but were limited by range and speed. Stationed on the USS Nimitz, 960 kilometers off Iran's coast, the Sea Stallions couldn't cover the 1,400-kilometer distance to Tehran without refueling. Helicopters, including the Sea Stallion, face constraints due to their rotor systems. As a helicopter moves forward, one side of the rotor advances while the other retreats, creating uneven airflow that limits speed due to shock waves and flow separation on the advancing blade tips. Despite being among the fastest helicopters, with a top speed of 360 kilometers per hour and a 1,000-kilometer range, the Sea Stallion required a refueling stop. The rescue plan, Operation Eagle Claw, involved 8 Sea Stallions refueling at a desert site called Desert 1, supported by 3 C-130 cargo planes. The operation quickly unraveled. As the first C-130 landed, a bus with 43 Iranian civilians approached, forcing soldiers to detain it. Then, a fuel truck sped toward the site and soldiers fired on it, causing a massive fireball that illuminated the covert operation. Meanwhile, the Sea Stallion Squadron, codenamed Bluebeard 1 through 8, encountered a sandstorm en route. Bluebeard 6's cockpit warning indicated a cracked rotor blade, detected by pressurized nitrogen sensors, forcing it to land and transfer its crew to another helicopter. Bluebeard 5 suffered electrical failures, reducing visibility and navigation, and turned back just 25 minutes from clear skies. With only 6 helicopters remaining the minimum needed, the mission pressed on. At Desert 1, the fireball and civilian presence added chaos. The sandstorm and heat damaged another helicopter's hydraulic system, dropping the count below the mission threshold. The commanding officer aborted the operation. This failure underscored the need for an aircraft capable of long-range travel and hovering, leading to the V-22 Osprey's development. Bell Helicopters had been experimenting with hybrid aircraft since the 1950s. Though initially less efficient than helicopters at hovering and less capable than airplanes in flight, NASA's support helped Bell develop the XV-15, a vertical takeoff and landing demonstrator. After Eagle Claw's failure, the Marine Corps greenlit further development of the 15-15 into the V-22. Over 2 decades, the concept evolved, with the first hover in March 1988 and fixed-wing flight 2 months later. Bell and Boeing produced 3 variants, the MV-22 for marine transport, the CV-22 for Air Force Special Operations, and the CMV-22B for Navy replenishment. The Osprey's defining feature is its Tiltrotor system. In helicopter mode, a fly-by-wire system controls the prop rotor blade's collective pitch for hovering, adjusts pitch oppositely for roll, tilts both rotors for pitch, and tilts them oppositely for yaw. This enables precise vertical takeoff, landing, and hovering. In airplane mode, the nacelles tilt forward, turning the prop rotors into propellers, with control surfaces like ailerons, rudders, and elevators taking over. A knob on the pilot's controls adjusts the nacelle angle, typically set at specific positions to avoid complex aerodynamics. Mechanical stops limit nacelle tilt between 0 and 97.5 degrees, with short landings possible at 60 to 90 degrees. A hydraulic motor and telescoping screw tilt the nacelles, requiring precise synchronization to prevent catastrophic imbalances during hovering. The prop rotors, with an 11.6-meter diameter, balance helicopter and airplane functions, unlike the C-130's 4-meter propellers or the Sea Stallion's 21-meter rotor. Their 47-degree blade twist enhances forward flight efficiency but reduces hover efficiency due to high disk loading, the ratio of the aircraft's weight to the rotor's area. The Osprey's heavy weight and smaller rotors produce a downwash of 80 knots, compared to a helicopter's 60 knots, complicating ground operations. The Osprey's intricate mechanics rely on 5 gearboxes and a shaft system. 2 Rolls-Royce turbines and an auxiliary power unit drive the system, with the shaft connecting the prop rotors through the wing's 13-degree forward sweep and 3.5-degree dihedral angle for stability and storage clearance. The tilt-axis gearbox ensures power transfer regardless of nacelle angle. Oil lubricates the gearboxes, doubling as a health monitor. As gears wear, they shed harmless fuzz particles, but larger chips signal failure. Magnetic chip detectors in the oil flow attract these chips, burning smaller ones with an electric pulse and alerting pilots to larger ones. In the Japan crash, chip detectors played a critical role. Gundam 22's communications indicated chip burn advisories. The flight log, recovered from the wreckage, showed 5 successful chip burns over 30 minutes. Protocol advises landing after 3 chip burns, but the decision is the pilot's. The crew, suspecting a faulty detector, continued. 3 minutes after the 5th chip burn, a chip too large to burn triggered a warning, requiring a landing as soon as possible or immediately if overheating occurred. The crew diverted to Yakushima, 15 minutes away, despite closer options. Voice recordings showed no urgency, and the decision wasn't debated further. As Gundam 22 approached landing, the left nacelle caught fire, causing a propulsion failure. The aircraft rolled and crashed. Post-crash analysis found no fuel or hydraulic contamination in the left nacelle. The chip detectors, surrounded by debris, were functional after cleaning. The prop rotor gearbox showed a broken gear and severe wear, with teeth nearly smooth. The crash led to a months-long grounding of the Osprey fleet, with limited flights resuming in March 2024, excluding carrier operations. This was the 4th Osprey crash since 2022, following incidents like a June 2022 clutch failure that killed 5 Marines due to unexpected wear and dual clutch engagement. The Osprey safety record has long been scrutinized, earning it the Widowmaker nickname. Since 1991, 25 incidents have occurred, 9 from pilot error, 10 from mechanical failures, 2 from both, and 2 under investigation, resulting in 58 deaths. Comparatively, the Sikorsky H-60 has had 390 incidents since 1979, with 70 deaths, 60 in the last decade. The CH-47 Chinook between 1966 and 2005 lost 238 lives in 10 non-combat crashes, but saw no deaths from 47 incidents between 2016 and per airframe. The Osprey's 0.025 incidents compare favorably to the H-60's 0.75 and CH-47's 0.11. However, its death rate per 100,000 flight hours is higher due to its larger capacity, increasing risk per crash. Complex aircraft like the Osprey often see early incident spikes which decrease as issues are resolved. The data suggests the Osprey's safety record isn't an outlier, though each crash underscores the risks service members face.